Assalamu alaikum, my dear student. Today our topic is energy of the simple harmonic oscillators. Energy of the simple harmonic oscillators. What is simple harmonic oscillators? A simple harmonic oscillator is an oscillator that is neither drumming nor damped. Means we observes what is the energy of simple harmonic oscillators. We know that we measure energy in joules. In two type of energy exist in simple harmonic motion due to changing positions or velocity. Means we know that the potential energy depend on the potential mgh and only and observes by changing positions and height we observe the potential energy, and by the variation of velocity we observe the kinetic energy. In a simple harmonic motions or oscillators, the position and velocity continuously change. Mean if position and velocity change, then energy associated with the system change from potential to kinetic energy. Means if we change positions or velocity, then also we observes or obtains what is effect on the changing of potential energy and kinetic energy. Okay, understand? For example, this is a linear oscillators, and this is mass and this is mean positions, and if we increases the spring onward mean positions, then is maximums, and backward from main positions negatives displacement. Means the spring, the potential energy depend on the spring. Means if we spring stretches are compressed, then we observe potential energy, and if we changing the block, this is block, then we observe the kinetic energy. Mean kinetic energy observed due to changing of block. Means if we changing block, we already know mass is m, and if we changing block means changing mass m, then create a velocity, then we observe kinetic energy. Mean kinetic energy is equal to half mv squares, and mass already given, and if we changing block, then we observe velocity, and we easily obtains kinetic energy. Okay, understand? Two energy we obtains in simple harmonic motion. First potential energy, then kinetic energy observes, and after adding kinetic and potential energy we observe total energy of the simple harmonic oscillators. First, potential energy. What is potential energy? We know that potential energy is equal to mgh, but here we observe due to spring. Means potential energy of a linear oscillator like that of figure is associated entirely with the spring. Means potential energy only we observe entirely with the spring. Mean its value depend on how much the spring is stretched or compressed. Mean linear oscillator, potential energy of a linear oscillator. Linear oscillator means only oscillator in one direction, like x directions. This is a linear oscillators. This is a k is a spring constant, and this is a spring, and m is a block mass m, and this is main positions, and if we increases the block toward x, then we observe displacement, maximum displacement, and if we backward from the main position, then we observe negatives of the displacement. First, to understand work done by spring, work done by spring on the block. Mean first we observe the work done on the block, then we obtains after finding work done, then we obtain potential energy. What is work done? We know that work done is equal to force over force dot displacement. Work is equal to force dot displacement is equal work. And if we obtains from the main positions to x, this is limit, and we divide displacement into small patches dx. Okay, and we know that F is equal to k minus kx. F is a restoring force. F is a restoring force. Restoring force, this force is equal to the magnitude of applied force but opposite in direction, and k is a spring constant. Put value of x here, we obtain this, and k is a constant. Only integrate on x. Only integrate on x. Okay. First, to understand how we integrate, means we integrate x की power n is equal to x की power n plus 1 over n plus 1. We integrate in this way, and we already know f is equal to minus k 0 to x. K is a constant. Integrate already value 1, then we add plus 1 in 1 is equal to 2 and divide with 2. This is limit 0 to x. Putting limit, this is final limit and this is initial limit is 0. Okay, we obtains this. Okay, is equal to minus half kx square. Okay, change in potential energy is negative of work done. Change in potential energy is negative of work done. We know that what is work done. Work done is equal to half minus half k x square. Put value here. We obtains minus use value of work done. We obtains this. We already write here. Minus minus plus. Okay. Now we use x is equal to xm cos square omega t. Oh, x is equal to xm cos omega t. Use square on both sides, then is equal to x square equal to xm square cos omega square. Okay, then use here. We obtain potential energy is equal to half k xm square cos square omega t. At the extreme positions, t we considered 0. Why we say that at the extreme position we considered time t? Means this is extreme positions. If block come on this point, this is main position. Means if we starting from main positions toward this point, time also considered, but here we considered only backward times. Again we consider times 0 because we only observed block toward this side. Then we considered time 0, starting again time 0. Okay, and if we put time t cos omega t and cos 0 is equal to 1, this value we use here, and we obtain potential energy maximum is equal to half kxm squares. And now we obtain what is kinetic energy. What is kinetic energy? Kinetic energy, kinetic energy only the kinetic energy of the system of figure is associated entirely with the block. With the block means this is block, and potential energy depend on spring and kinetic energy depend on block. Its value depend on how fast the block is moving, that is on Vt. That is on Vt with respect to velocity. How block is fast, then we observe kinetic energy due to changing of velocity. Okay, we know that the kinetic energy is equal to half mv square, and v is equal to x m square omega square sine square omega t. How we obtain this value? We know that x is equal to xm cos omega t, the derivative of x with respect to time t. Xm is constant and derivative of function cos omega t, because cos depend on t. Then we know that the derivative of cos with respect to time t is equal to minus omega t. Then derivative of omega t is equal to omega. This is omega. Okay, and we know that the rate of change of displacement is equal to velocity. This is velocity, and after scaling on both sides we obtain this, and after obtaining we using the value of velocity in this equations. Okay, kinetic energy is equal to half m omega square xm square sine square omega t, sine square omega t. For maximum kinetic energy we considered sine square omega t 1. Then we write here, we know that k is equal to m omega squares, use here. Then we obtains kinetic energy maximum is equal to half k m squares. Okay, we find kinetic energy and potential energy. Okay, this is equation 2. Total energy is sum of kinetic energy and potential energy. This is potential energy and kinetic energy. Here we use value only for with the times, not we considered maximum value. Okay, we considered proper value with the variation of sine times and sine cos and sine theta, means we use the functions with the time variations. Okay, potential energy, we know that potential energy is equal to half k xm square cos square omega t plus, this is potential energy and this is kinetic energy. This value use here. Okay, and we know that the omega is equal to k, we use here, and half k xm square common in both value we take in common, and we know that this is a trigonometric functions and is equal to 1. Cos square omega t plus sine square omega t is equal to 1, we use here, and this is a total energy in simple harmonic oscillator, in simple harmonic oscillators. Thus the total mechanical energy of linear oscillator is indeed constant and is independent of times and positions, time and positions. Okay, and also we obtains. Okay.